This is the mic.
Oh, so we need to turn it on?
Usually it's on.
Oh my
Okay.
god. Okay, so we turned it on
But
and it
also the
works.
battery of this is empty, you know, that's what you. Thank you.
Okay.
You could have
so
thought of that.
we forgot to turn it on.
Okay, now people hear us, right?
Why do I hear myself? Now
Okay,
it maybe
I
work.
think now everything should work and go ahead.
Okay. Thank you for your patience. What was I trying to say? Yes, I'd like to thank Evado for funding my trip here. I'm here as part of the Autonomous Agents thematic semester. And I'd also like to thank the Willem Foundation in Denmark. I have no way of imagining that this research has anything to do with improving the physical windows that we install in our buildings, but I'm grateful that they sponsor my research. So thank you. I've been here for almost a month and I'm still meeting people, so I wanted to introduce myself. I'm from the north of Scotland. I grew up next to Loch Ness and I've never seen the Loch Ness Monster, but it may still exist. I studied for my PhD at the University of Edinburgh, and then I moved to Amsterdam where I was a postdoc for 2 years. And since 2018, I've been at the University of Copenhagen in Denmark. More broadly, I work on things other than multilingual language models. Earlier this year, we had a paper on mechanistic interpretability, trying to understand whether LLMs are using similar mechanisms to do factual recall. Just yesterday at EMNLP, one of my PhD students presented a work on synthetic data generation using retrieval augmentation to control and ground the process. I've also got some work on multilingual, multicultural vision and language understanding. In this case, it was fine-grained understanding of Chinese cuisine. And I've also got some recent work on test time scaling and small vision and language models, where none of the things that seem to work for larger models seem to transfer into this. So if you're interested in any of these topics, please feel come talk to me after the presentation today. But I'm not going to talk about any of those things. I'm going to talk about how can we create high quality NLP for all written languages, which is a lofty goal. When we talk about all written languages, we're usually meaning 3,000 different written languages across the world. And NLP tools typically cover 100 languages based on how large these were in Wikipedia back in around 2014, 2015. And this results in technological exclusion for billions of people around the world. If we take this plot from Joshi's paper in 2020, if you are part of the succeeding languages in section 5 in the top right, you can expect high quality NLP tools. Whereas if you're in one of the languages that is struggling or left behind down here at zone 0, 1, and 2, NLP tools are not great for your languages. And maybe some of you have experience of that yourselves. One of the things that often comes with the lack of good access to technology is that you'll have to pay more in order to use these tools. There's been a lot of discussion about this idea of tokenization costs, where if you want to process text in Tibetan or Georgian, you might have to pay 2 or 3 times as many tokens for your inputs, which will matter if you're doing either local work with small language models or you're paying for API-based tools. So why does this happen? Well, let's go back to the start.
Just quick now that the mic is working. If you have a question, please wait until I bring the mic so that people online also hear you. But feel free to ask questions in between or online.
Okay, I will try to keep track of the questions. So NLP is a pipeline, and I think most people here probably know this, but it's worth rehearsing. So if we start with a simple sentence like Kierkegaard was a golden age philosopher, we will typically then normalize this to split out punctuation, and then we'll tokenize it. And in this example, I'm using what's a very bad tokenizer for Danish. It's going to split Kierkegaard into 3 subwords, which is not useful because Kierkegaard is a well-known philosopher, and you should be able to represent this using a single input, instead of relying on your composition function to compose all of these representations together. After that, we will associate each of these subword tokens with an embedding vector, which is the input to a model that you might use for fine-tuning or prompting. And everything goes wrong here at the second step in the traditional NLP pipeline. So why is this a problem? It's because language processing is an open vocabulary task. There was some point in time in which Google was not a word that was in common use. And so n-gram language models that were being estimated over counts and vocabularies in a corpus had to deal with this through a back-off mechanism. More recently, a word like COVID was not in common use, but we all know why. And then all of our language processing systems needed to deal with this, preferably as a single input. Or maybe even more recently, a word like skibbity, which has who knows what it means. NLP systems will probably have to handle this, and soon it might become its own unique token within a tokenizer. So how do language models typically deal with this? Would they either use a trained vocabulary over a corpus using something like byte pair encoding, where unseen tokens are going to be handled with something like byte level backoff? Or you can have a corpus-independent approach where you define all of the units in advance, for example, based on Unicode characters or UTF-8 bytes. And this approach actually results in what's known as the tokenization tax. So this image from Sina at ETH Zurich shows that the same input text given in English is going to be about 50% longer if you process this written in Italian, which doesn't seem so bad, but it's not ideal. But if we try to use this in other languages like Central Kurdish, or in the top right-hand corner here, Shan, you're more than 10 times as many tokens to represent the same input due to how the tokenizer deals with that. I don't think that's right, and that's something we should strive to solve as natural language processing researchers. You can ask yourself, where's the sweet spot? And it's kind of a continuum here. On the one side, you can have full language coverage by dealing with really long sequence lengths using something like bytes or characters. On the other hand, you could have really large vocabularies using something like BERT, the modern multilingual BERT, or Word2Vec, which is now very old, but I think it has the largest vocabulary of any language model I've ever seen. And so the sweet spot is probably somewhere along this axis, unless you want to have an alternative. And that's what I'll talk about today. So my alternative is to treat language as visual data. We're going to take the classic NLP pipeline and throw everything away, because that's a good place to start. Then we're going to just render text as an image and give this directly as the input to a model. So if we take a piece of Amharic text, like this sentence, which to the best of my knowledge reads, Ethiopia is a country in East Africa, you can render this easily into a blank canvas and give this as the input to a language model. In this case, we pre-train our models by randomly masking the input data. But in this way, we can support any language we can typeset. So we don't have to pay prohibitively large costs for longer sequences. Why are we doing this? Well, it's inspired by a few different directions. In 2021, Liz Selesky and colleagues showed that you can learn a translation model by having visual representations of text in the encoding representation. And this is connected to a standard tokenization-based decoder. So that was a good initial starting point. Kai-Ming He and colleagues showed in 2021 that you can learn a visual representation model by randomly masking patches and learning to reconstruct those patches at the pixel level. So you don't need any label supervision to do this. You don't need contrastive objectives, you just need reconstruction of the visual input space. The third piece of inspiration came from about page 36 in the CLIP paper, the archive version, not the conference version. There's a small table of results about how using the CLIP model, you can fine-tune the visual representation of that, the vision transformer, to perform semantic sentiment analysis. And so that made me think maybe we can go even further and get rid of the requirement to ground against image data. There's a lot of related work that's appearing now in this area, so I just want to briefly cover it before I focus on the work we've been doing in my group in Copenhagen. I'm going to split the related work into 3 areas: that based on transduction, the work based on what I call more representation learning, and work based on the compression of visual data. So from the transduction side, we've seen, for example, Zalewski's work on visual representation learning. At Column a couple of weeks ago in Montreal, there was the pixel fallback model, which showed how to integrate visual representations into existing LLMs. And from Google research was the Pix2Struct approach, which learned visual representations by trying to decode HTML representations of web pages. From the representation learning side, we have our work from Copenhagen on pure pixel language modeling. There's also some work from DeepMind on language image contrastive learning using something like Clippo, which renders text and has rendered images as well from photographs. And also the Pixar model from the University of Edinburgh and Heriot Watt. There's also some work at the intersection of these based on trying to jointly learn from self-supervised representations and transductions using approaches like Pixel GPT or Seeker or PEEP. From the compression side, this is an emerging area. There was a paper, I think maybe last year at NeurIPS on visual compression representations, or just yesterday on text or pixel compression representation at EMNLP. And right in between those, we have DeepSeek OCR, which is primarily trying to focus on the idea of compressing visual inputs for the task of transduction of OCR outputs. And in addition to this, there's been a lot of analysis and evaluation work on using this to model different dialects or to work on diacritic restoration, trying to estimate the robustness of inputs to perturbations, uncertainty estimation, and also a line of work on what you could call pixology, trying to understand what these models actually learn. In the remainder of the talk, I'm going to cover 4 different areas we've worked on. And so I'll just get started straight away since we had a bit of a late beginning. Our first effort in this area was published at iClear 2023 in Rwanda. So the pixel language model starts with a collection of text on disk, like you would have if you downloaded something from Hugging Face datasets. And then we use open source libraries. In particular, we use Pango Cairo, which is a rendering engine installed and available in most Unix operating systems, and Google Noto fonts, which is an open source font package that will cover more than 100 languages, including ancient languages as well. And we render the text directly into patches, as I'm showing here. Then this is projected into an embedding space, and we have positional information added to those input representations. Some of the patches are randomly masked, and we do this over a span of patches instead of randomly masking everything. This is so we hope that the model learns kind of word-like representations instead of learning arbitrary pixel reconstructions. The unmasked data is processed by a 12-layer transformer encoder, and then the masked data is reconstructed after everything goes through an 8-layer transformer decoder. I'll give some more details about different parts of this model in a couple of minutes. So I'll start by talking about the text renderer. It's super flexible. We can render full RGB data, including emojis. We can handle left to right and right to left writing systems, and also logosyllabic writing systems. And for tasks that might require word level representations like dependency parsing or part of speech tagging, we can start each word within its own unique block. In terms of the actual rendering of the data, pixel representations are compact. They don't explode sequence lengths like you might see with things like byte representations. In this plot here, I'm showing on the x-axis the length of an input, either in terms of subword tokens or patches, and the y is the distribution of the actual data we observe. And this is from the universal dependencies tree banks, so the segmentations are created by trained linguists. In this case, for Turkish, we can see that the reference data is much more compact than anything else. But for example, Pixel is competitive with mbert and BERT in terms of its tokenization length. If we expand this out to look at 9 languages in total, then something is quite obvious here. The pixel representations shown here in pink are generally quite compact. If you look at Arabic scripts in the top left, there's no representation penalty at the input layer. Or if you look at Turkish or Japanese, it's also the same story. I want to point out here that in the bottom left, BERT and MBERT have BERT has really good representations of token lengths for Korean, but that's because everything is UNC. And so it's kind of trivially cheating in order to reproduce this sequence length. So with pixels, you're not paying length penalties, unlike you might see with other representations of inputs. How does the patch embedding layer work? So it's a convolution layer where we have a 16 by 16 by 3, so an RGB space input representation. And then we have a set of 768 kernels. And the intuition I want you to have is that each kernel kind of takes a snapshot of the input. And this gives us a 768 dimension representation of that physical patch that's going into the model. And we do this simultaneously over all of the input patches. But unlike kind of standard convolution neural networks, it's not a sliding convolution over different parts of the input. It's only looking locally within its own patch. And no talk about convolutional network representations is complete without imagining what might actually be happening inside the learned filters. This is a video. It might take a few iterations for you to see that, of all of the different kernels, the 768 kernels inside of the model. It's going from the pre-training at almost the start of the operation until when we finish pre-training at 1 million parameter updates. So some of these kernels seem to be learning directly about the presence or absence of pixels. It's like they're learning about white space blocks in between words, or maybe some other extra white space that appears. There's a collection of kernels that seem to be focusing on horizontal strokes that stretch across patches because we have unconstrained rendering of the input data. And finally, if you look really hard and you try to convince yourself, there are some kernels that seem to be catching curved shapes that go from one patch to another. So this might be things like the letter B or the letter A or the letter E that regularly will extend itself across patches. And I'll point out here, but I'll reiterate again, this model was only pre-trained on English data. So that's why I believe that these are these types of shapes. In terms of the training, we go through the transformer decoder stack, and then we train the model using a mean squared error objective on reconstructing the unobserved patches from the input representation. So there's no softmax normalization here. There's no substantial increase in the cost if we want to pre-train on more languages because we're not having a larger vocabulary in the representation. So before I start to show some experimental results, I would like to claim some of the benefits here. This representation allows us to process anything that can be rendered into a canvas. We have open vocabulary support, given the font libraries that we're able to use. We can support almost any written language. And we also have some great flexibility to process other forms of data, for example, scanned PDFs or more historic contexts. And unlike language models that are based on subword tokenization, we get complete parameter sharing from the input to the output. And usually when you have a tokenization-based model, some parts of your subword vocabulary are not updated very frequently because you have low frequency inputs. Here, everything is updated all the time for all inputs. I want to demonstrate some reconstructions that the model does through its generative process. On the x-axis here, this is the number of steps for pre-training the model, and going from 100,000 steps up to 1 million steps. The input document is about penguins and how they have evolved to have streamlined body shapes. The model did not see this document during pre-training, but Philip really liked this as an example, so we used that. Here in blue, I want to highlight some improvements the model experiences in its reconstruction. So along the top here, we can see that the model goes from being very uncertain about what to produce in the inputs to saying that penguins have long legs. It reconstructs this missing piece of text really quite cleanly. And down here at the bottom, by step 500,000, the model produces the sequence, this gives the clusion, and clusion is not a word in English. It doesn't exist. I've looked this up. It just fits in the space. But after a million steps, the model realizes that's not right. I'm going to talk about illusions instead of occlusions. It doesn't always work, though. There are some parts of the reconstruction that don't really improve, no matter how long you pre-train. What you can see is that the model is simultaneously rendering many different letters at the same time, expressing its uncertainty about how to produce this output. So how was it pre-trained? We only pre-trained it on English. We used exactly the same data as the BERT language model. And we trained it in 2 days on 8 A100s. So this is not necessarily the work of the GPU rich. You can do this on lower resource settings. Our model is quite small. It has about 100 million parameters. And when we fine tune it for tasks, we throw away the decoder. So it only has 86 million parameters in the input. There is a small amount of non-English text in our pre-training, as shown by Blevins and Zettelmeyer in 2022. But it's really a trace amount. And I wouldn't claim that you could learn, for example, Chinese language by training on the additional symbols that appear in Wikipedia about the translation of the Great Wall of China into traditional Chinese. So we evaluated this model on a set of different downstream tasks that are really common for natural language processing research. And we compared against 2 models. I know there are other models out there that we could compare against. I am familiar with the literature, but in this case, we wanted to compare against a model that had basically the same pre-training setup, or try to solve exactly the same problem as we did, but using UTF-32 code points instead of pixel representations. In this case, BERT is also only pre-trained on English, but Canine is pre-trained on 104 languages extracted from Wikipedia. So we could expect Canine will substantially outperform Pixel based on what it's seen and the representations it's been able to learn. If we start with the dependency parsing results, in this case, on the x-axis, I'm showing the unknown tokenization rate of the BERT language model, and the y-axis is showing the F1, the labeled F1 for dependency parsing. The main thing to take away from this is that Pixel vastly outperforms BERT for unseen scripts that cannot be tokenized well by the model. So if we take something like Coptic, where the UNC rate is 94%, you actually can't really do dependency parsing when 94% of your inputs are UNCs. That's basically an unsupervised parsing problem. But if you look at something like Hindi, Hindi has a 33% UNC rate, and Pixel still outperforms it much better. The same for Japanese. Whereas when we have more kind of matched languages like English, Arabic, and Vietnamese, the difference between tokenization-based representations and pixel representations doesn't stand out there. If we go and look at a task like named entity recognition, in this case on the Masakana NER dataset, here now I have BERT in gray, Canine, which is the 104 language pre-trained model in green, and Pixel in dark blue. So Amharic is the only non-Latin script in this evaluation set. BERT can't do any named entity recognition on Amharic because everything is UNC. But Canine, which is multilingually pre-trained, still doesn't outperform the Pixel model. And actually, when you look across the spectrum here, Pixel generally outperforms this multilingually pre-trained model, even though it's only seen English during its initial training step. It's not all great. When we evaluate the model on sentence level understanding, for example, in the glue task, we can now see that BERT, with its tokenization-based representation, has better sentence level representations than Pixel. There could be many reasons for that. It might be because the original BERT model was actually trained with pairs of sentences and it had a specific sentence representation learning part in the model. Or it could just be that pixels are a suboptimal representation for sentence representations. I'll come back to that later in the talk. The final evaluation I want to highlight here is the robustness of the model to adversarial attacks. So Selesky initially showed that Pixel models in her machine translation work were very robust to things like orthographic attacks. In this case, this is for natural language inference using the Zero dataset. And there's 10 different types of attacks you can have here. I just want to highlight 2. So when you attack the inputs using confusable characters, BERT really suffers when you do this. As the attack strength increases up to 80%, it degrades down to nearly 40% accuracy. But Pixel can maintain up to 60% accuracy in the face of all these confusable characters in the input. Another one here is the robustness to phonetic attacks, where you replace the standard orthographic version of the input with a phonetic rewriting of it. So a model like BERT is going to really struggle here. It's never seen phonetic representations of words. It's trained over orthographic representations scraped from the web. Whereas Pixel is a lot more robust to this because it hasn't committed to any type of tokenization. It doesn't commit to the representation of a word, and it can more easily adapt to that. Nevertheless, when we finished this project, we realized we kind of did most things wrong. There's a question before I tell you what we did wrong at the back. In between here, you can ask questions.
I would like to spend a bit of time on the architecture. Can you go back, please, to the architecture?
Sure.
Yes. So why do you need the decoder here? Like you could train this entire thing without the decoder, right? Like we could, if you just have the encoder, you're patching something and then you're predicting some masked tokens here. You have the embedding of the masked token.
You mean after the transformer encoder layer?
After the transformer.
So after the transformer encoder layer, we insert kind of position identifiers for the patches that need to be reconstructed. And the decoder is responsible for trying to reconstruct the pixels.
So can you explain how the two parts here, like one is the encoder part, like so you could throw away the decoder if you want and then train just the encoder part.
You can try. We do have experiments
Oh,
on throwing it. Well, we never threw away the decoder. We tried to compress it down to maybe just one transformer layer or two transformer layers. But what we found is that in order to get a good signal for updating the encoder representations, we needed some depth in the transformer decoder so that it could attend over the encoded representations of the data it observed and use this to predict the pixels of the data it did not see.
Okay, I see. And can you tell a bit more about the reconstruction process, the transformer decoder? So how do you reconstruct the patch? So you can reconstruct the embedding for the patch, but what I'm struggling is, okay, so if you take here, right? So you have xi minus xi hat. Xi is the embedding, is that?
This is the true observed patch that should exist.
Oh, that's the patch.
Yes, it's the literal set of pixels that should have been in the input.
Oh,
and xi hat is what the model tries to predict through this linear transformation into the 16 by 16 by 3 pixel space.
Oh, I see. It's directly the pixel representations. Xi is just the pixel.
Yes.
There's another question.
Can you go back to your diagram where you show your model, encoder, decoder? Yes, this one. So here, my understanding is you have this pre-training phase, which is reconstruction, and then you have several downstream tasks. Do you fine-tune the encoder, decoder to perform the downstream task? And do you fine-tune them with the class token? So I guess my question is more broadly, what's the procedure for fine-tuning this pre-trained model on the downstream task?
That's a great question. So what we do is we throw away the decoder because we don't need it anymore. The decoder exists just to learn the representations in the transformer encoder. And then if we want to do something like a sentence level task, like glue, we're going to fine-tune the CLS representation. If we're going to do a token level task like dependency parsing, then we're going to attach a classification head around all of the different word level representations we get from the output of the transformer encoder. And for fine-tuning, none of the data is masked, it's all observed. Does that answer your question?
So here, my understanding is the encoder and the decoder during the pre-training is the same model, and then you chop off the head of the decoder, and then you do the fine-tuning.
Yes, and so coming back to the previous question, that's why we experimented with different depths of the transformer decoder, because if we can make it shallower, we can pre-train faster. But you need a certain amount of capacity in that for the model to really learn how it should reconstruct the input data. Okay. So let's get back to me telling you why we did things wrong, or how we did things wrong. So at EMNLP in 2023, we tackled this problem of text rendering. Once we finished working on the paper for iClear in Rwanda, we took a closer look at the types of inputs we were giving to the model. And this is the set of top 10 patches that the model observed during pre-training. And something here looks quite wasteful. This is not a type of visual variance that you want the model to have to learn from. It's a bit naive. And so we wanted to know if we could do any better than this. We explored a few different rendering strategies. So the first one is the continuous rendering, which is the one that I told you was wasteful. The second is to do structured rendering, where we try to control the model so that it renders bigrams into patches and starts words where this is necessary if you have information about white space separation. Otherwise, we'll just render bigrams as we need along the way. It's also possible to approach this from the perspective of monospaced rendering, which is shown in the third option, but this doesn't work very well for languages that require diacritics. You're going to end up with all kinds of problems there. And the final would be having word-based rendering, where each word will start in its own patch. If we look on the x-axis of the number of sentences observed to the number of unique patches, yes, indeed, our original rendering strategy was hugely wasteful. If we go down a little bit here in the blue dotted line in the middle, this is word-based rendering. So that kind of keeps things under control, but we still see nearly 100,000 unique patches across 10,000 sentences. Whereas using bigrams or monospaced font rendering, it's very flat in terms of the number of unique inputs the model sees. And that should be a useful signal to improve the quality of the model. And so we adopted this bigrams rendering strategy, but we have many more examples of experiments and ablations in the paper for more details. And so if we take this and we pre-train the model on exactly the same data as the model I just presented, and we then fine-tune it on something like GLUE, which is this English sentence language task, then it's much better performance just by taking this one small representational shift. Now we are almost reaching the performance of BERT, and we're the same size of model and the same pre-training data. So bigram rendering really does improve the representations that you can learn from this. It also allows us to do something that's not very fashionable, but I'm really into it, which is scaling our models down. Everyone is talking about scaling models up to 7 billion or 30 billion parameters, but I'm interested in building language models for all the written languages in the world. And I think for ecological validity, we also want to have small language models that people can use on lower compute devices, rather than expecting everyone just has an H100 that they can easily use. So in this case, these are aggregated scores across our dependency parsing, sentence understanding, and QA benchmarks. The orange one is the bigrams version of the pixel model at the same number of parameters, but we can do pre-training on models as small as 5 million parameters and get quite competitive performance compared to our 86 million parameter model. Or if you really want to retain the full performance, you can go to 22 million parameters. And this is not distillation from a larger model, this is pre-training from scratch. So it's pure representation learning, nothing is being guided along the way. There's a question?
I want to ask, but have you done distillation?
No, we're doing it now.
Oh, okay, nice.
So this morning at 4 a.m. Montreal time, Ilker presented this work at EMNLP, which is our first attempt in doing multilingual pre-training of these models. So far, everything I've spoken to you about has been monolingually pre-trained. In this case, we used exactly the same architecture and hyperparameters as the previous models I described, but we pre-trained on 4 visually diverse languages. So we're pre-training on English to cover Latin scripts, simplified Chinese for Han, Ukrainian to cover Cyrillic scripts, and Hindi to cover Brahmic script languages. The model here is pre-trained where a batch will have many different languages within it, but it never has to do reconstruction within an instance across different scripts. And is pre-trained with the same kind of pixel reconstruction objective. Everything else is fixed. The data is different because we're now splitting it across 4 languages, and we're training for the same number of parameter steps. So now that we're training on more languages, we need to do evaluations in a lot more languages. We turn to the SIB200 dataset from David Adelani. This is the simple inclusive benchmark dataset for classification. And if we compare the performance of our English-only pixel model to our multilingually pre-trained model on 4 languages, we get a 12 percentage point boost across 23 different languages. We don't quite reach the performance of Canine, but that was pre-trained on 104 languages. So I still think this is a reasonable step in the right direction. And if we look at some of the results in more detail, here's a specific focus on the Brahmic script languages. So Pixel M4 was trained on Hindi, which is the middle bar, and we can see there in orange that it performs really well on that. But we also get good transfer into Bengali and Tamil and Telugu, even though it's not been pre-trained on any of these languages. If we look at Latin script languages, Pixel M4 was pre-trained on English. And if we compare this to Pixel Bigrams, it's basically the same performance, even though it's only seen a quarter of the English data that Pixel Bigrams has seen. And when we look across the other Latin script languages, there's not much improvement to be found there. And the Canine model outperforms across all of these Latin script languages. We can also look at the CJK languages. So we pre-trained on simplified Chinese, and that gives a big boost in performance for that. We almost reach the performance of Canine, but we also get big boosts here for Japanese and Korean. I know there is character sharing between simplified Chinese and Japanese, but the transfer into Korean is particularly interesting and worth thinking about in more detail. If we look at the dependency parsing performance here, the main message is that multilingual pre-training improves performance for non-Latin scripts, even for languages we didn't pre-train on. And why does this happen? We did some analyses, for example, using LinSpector. If we look at different languages, we can look at things like how are case markings predicted by the word level representations in our model. And so if we take Bulgarian, which is a Cyrillic script language, then the M4 model is much better than the English-only model in this case, across all different layers when we take these word level probes. Whereas for a language like Finnish, which is notoriously expressive in terms of its case marking, we don't see much improvement in performance from that respect, but it doesn't perform worse than English-only pre-training. Whereas if we look for something like tense understanding, in Polish, we get improved performance from multilingual pre-training on 4 different languages. And we also get improvements on Greek, which is a completely different script that's unrelated to the Latin script. So there does seem to be something that's better learned internally inside this model. And we can also measure the sentence representation 0 shot after pre-training. In this case, up here in the orange, we can see that the English sentences encoded and the Ukrainian sentences encoded are very good nearest neighbors for each other in terms of recall at 5, 0 shot. The English Hindi sentences are a little bit worse, whereas the English simplified Chinese sentences in green are much lower in terms of their 0 shot retrievability. We don't fully understand why this seems to be the case. It seems that performance going through simplified Chinese or Ukrainian or Hindi is much less powerful than English, even though they've all seen the same amount of pre-training data. This definitely deserves more attention. And we can also look at reconstructions of the text. I'm not going to claim these are good reconstructions. This is a collection of random articles I grabbed from the web. The first one is the Wikipedia page on simplified Chinese. The second is some kind of newspaper article about the European Union and Ukraine. The third one is a Ukrainian newspaper article. I don't even know what it was about. And the fourth one is a story in a Hindi language newspaper about, I think, a movie star who was apologizing for infidelity. Now, these are not the types of different inputs that should be lending information to each other. But one thing I want to highlight is that if we look within the Hindi text or within Ukrainian text, it's doing localized reconstruction of scripts that are appropriate for the inputs, even though it can attend anywhere in the visual representation space. And we didn't train it to do this. This is something that it has learned by itself through the pixel reconstruction loss. I have one more part of the talk, and this is more of an applications perspective. I want to warn you that there are parts in this that contain dataset samples that are racist. They will be shown in orange. If you don't want to look at them, you don't have to. I'll do my best to avoid describing them in detail. This was a collaboration to work on processing historical documents. There are huge efforts to try to do this around the world, and typical pipeline is you'll scan your documents into really high quality formats, massive images, and then you'll perform OCR over those images and pray that the OCR is correct and useful. And then you can search through these OCR documents using standard text interfaces. And we wanted to know whether you could do this without the OCR step, just working directly on the visual representations. We had a collection of newspapers from the Caribbean, and we were collaborating with researchers who were interested in tracking notices in newspapers about escaped slaves. And so they wanted to collect aggregated statistics over things like what was the given name, or what was the reward offered for an escaped slave, or who was the named contact that you should reach out to. And so they had a data set of 1.5 million scanned newspaper pages. And so the first thing we did is we did what we called historical document-aware pre-training, where we faked Wikipedia and the books corpus by trying to make it look more like a newspaper by having different fonts as part of the training, some distortion in terms of the representation of the input, some salt and pepper bleed through from the back, which you also might find in large scanned collections of historic newspapers. But the pre-training was exactly the same as everything else I've described here. And then we framed this as a visual question answering task. So we initialized a canvas and we rendered the question using our font libraries, and then we pasted in the actual newspaper snippet. And we trained the model to predict the patches where the answer could be found. That was it. There's no OCR anywhere in this for our model. And if we compare this against a BERT-based model, which is trained over professionally transcribed text, the model performs surprisingly well, given that it has not observed any of this direct linguistic supervision. In one of the examples, I'm trying to highlight the fact that the model is giving a lot of its self-attention to the part of the image where the information about the reward offered is located. And I'll read it out to you. It just says that you will be handsomely rewarded for the information. This is not a monetary value. This is a much more abstract way of expressing a reward. In the second example, the self-attention is attending to a person, but it's the wrong person. So it knows what the text of people looks like within the input, but it's just not localized the correct contact person within this. So I'm reaching the end of my talk. Today, I wanted to convince you that general purpose transferable representations of text can be learned directly from visual inputs without additional linguistic supervision in the model. And that if you carefully consider how to structure the input of the rendered text, then you can get easy improvements in performance. And that multilingual pre-training clearly gives improvements without any architectural changes or other changes to hyperparameterization of how you train the model. In terms of future work that I think is worth investigating, I've got 3 possible directions. One is more of a theoretical consideration. Like, why does this even work? We know, if we think about masked language models, that this is a classic distributional semantics problem that we've known about for a long time. And we can develop stories about why this would learn good representations of text. But why can you learn good representations of text if you're reconstructing pixels that represent characters or the space in between characters? So that's one thing. I'd love to hear people's thoughts on that later. We're also doing some work in terms of architecture. So we're now investigating hybrid designs where We have an open science collaboration that everyone is welcome to join if you have the time or interest. Everything you need is down here on the GitHub page. And we also have some of our own compute if you have specific ideas you want to experiment with. The main idea here is to encode data using image representations as input into a latent transformer, and then to have small transformer decoders that produce symbols and outputs at byte representations. So the small transformer decoder is not really going to affect the cost of self-attention of the latent transformer decoder, which is going to work over these more compact representations of the visual data. The other thing is, I think it's kind of important to rethink what it means to be generalizing across different languages and scripts. And I'm really curious about whether pixels enable visual transfer. In this case, English and Italian could give you visual transfer to all Latin script languages. That's one hypothesis you could form. Or Hindi will give you visual transfer to all Devanagari script languages. It's also possible that what you actually get is something more similar to grammatical structure transfer, if that's what these pixel models actually learn. So we could imagine this being useful for other Germanic languages, or Italian being useful for other Romance languages, or Hindi being a useful starting point for other Western Hindi languages. This is something that we don't know yet, and I think we want to carefully consider this going into the future. So I won't repeat my conclusions. I hope I've managed to convince you that this is a new type of language model that's going to tackle open vocabulary processing using render text instead of tokenization. And since we're running out of time, I'm happy to take some questions now.
Okay, thanks so much for the great talk. I really enjoyed it. I was also trying to think about why this might work as you were presenting. And I wonder if it's, whether you think it's due to something specifically about the pixel domain and the visual modality, or is it about better parameter sharing between these, the I guess, letters or bigraphs, which are like these discrete symbols, right? So maybe the fact, just the fact that there are curves in the visual space means that it's much easier to share parameters across the inputs.
I think we're thinking in the same direction. So part of the story I tell myself is that if you take a language like English and you do pre-training on this, you're going to learn about visual structures that are going to occur in, for example, simplified Chinese or in Cyrillic. They're not exactly the same, but the convolution filters have learned, oh, there's a horizontal stroke on this side of the image. I can take advantage of that. I'm not sure how to design the experiment to clearly show that this is what happens, because at the moment we're trying to go more into the multilingual representation learning space. But maybe we could try some kind of representation that could uniquely represent text, but not have the characteristics that we associate with orthographic writing. But then I think that maybe all my PhD students would lose their minds and they'd rather work on something else.
Thank you for the great talk. Also, I found it very interesting and enjoying to watch. So pushing a little bit on those questions, and also the last question you asked about the transfer learning and generalization. You could argue for the same reason that you just said, that if you took a model trained on large-scale images like a clip model, which has seen natural images, it also has seen text, but you could make the argument that because of the natural images it has seen, it has learned to maybe capture edge detectors and other type of higher level functions that could be useful for the kind of test that you are thinking about. So going into that line of argument, do you think it would be interesting to try playing with these pre-trained model and see whether you would see positive transfer and potentially better generalization?
Thanks for the question. I didn't cover this in the talk, but in some of our initial experiments, we tried what you call the simple baseline, where we took the clip visual encoder off the shelf and we tried fine-tuning it for these tasks. It doesn't perform nearly as well as the representations that we can learn from self-supervised training over language data. And there's actually a paper I saw at CVPR earlier this year that says, if you do your best to remove all of the images from a pre-trained clip from the pre-training of a clip model that might contain text, then the model has no text understanding whatsoever. It's something that is directly baked into the model during its pre-training.
Okay, I have actually also one more question. As someone working on visual language, I think the domain where I see this most useful is like more like reading in the wild. Like if you're at Times Square and you have all these like signs of like things, like really hard images. You have a bit of that already with the newspaper, but do you have seen any work or like have worked with this yourself, like situations where like the images are like, it's like natural images almost, like your Times Square, let's say?
We haven't done that yet. And even though I'm very grateful to the Willem Foundation for supporting my work, they don't quite give me enough resources to hire all the people I'd need to also go into the natural photograph perspective of this. I also think that then you maybe get a bit closer to OCR type problems. And I mean, that's very interesting, but in that case, you require direct linguistic supervision from the best of my understanding. But maybe if we had a huge data set of these types of images from photographs that contained text but no OCR, we could use that for much larger scale pre-training, and that would be super cool.
Nice, yeah. All right, any more questions? Yeah.
Can you like compare and contrast this approach to like tokenizer free, such as like the work of Luke Zettelmoyer? Like, do you have any intuition as to why this works in the perspective of that, or how these two methods like differ?
So I think you're talking to the byte latent transformer that was at ACL 2025. So the byte latent transformer is also trying to solve the tokenization free problem. At its core, it still kind of has a tokenizer. It has a discrete vocabulary of 256 units. But I'm not going to labor that point. I think that compared to other tokenizers, it's very universal. And the byte latent transformer is also trying to operate over these really long sequences of inputs. I think I remember what they were talking about in Luke's talk, their sequence lengths are enormous for pre-training, even though they're not observing much text in terms of the like raw white space separated word representations. I also think that the BLT work, which is really fantastic, they were focusing a lot on scaling this up to like the 7 billion parameter size and showing that this was directly competitive against tokenization-based 7 billion parameter models. This is not yet part of the focus that we're trying to pursue, but I have a lot of respect for the work.
Okay. If there's no more questions, then again, thank you, Desmond, for the great talk. And yeah, also thank you for visiting, I guess, Mila and our group. It's been a great month having you.
Thank you.
And yeah, cool. Thanks all for coming.